Chapter 2.5 is optimization problems. So for optimizing, what this means is we are going to be maximizing or minimizing a certain quantity. And to do this, we're actually going to be using the concept of the derivative. So I threw a couple real life examples on here. This stuff pops up all the time. A couple examples of this in real life are an airline must decide how many daily flights to schedule between two cities to maximize profits. So you see the word maximize, so that means it's going to be an optimization problem. Another example is that a doctor wants to find the minimum amount of a drug that's going to produce a desired result in one of their patients. So these are real life examples or applications of optimization problems. So what we're going to be doing is we're going to end up taking a derivative and setting it equal to 0 and solving for x. This is because when we do that, we have the relative max or relative min is going to be the x value when we set the derivative equal to 0 and solve for x. And then we just have to make sure that it is a relative max or min by setting up the number line like we did in the previous sections. So the way that we're going to be doing it is we're going to have two equations with two variables. One equation is going to be called the objective equation. And the objective equation is going to contain the variable that we're trying to optimize. And then we have the constraint equation. The constraint equation is going to be placing a limit or a constraint on the way that the variables can vary. So before we get into how we're going to be doing this, we're essentially going to be having, like I just mentioned, two formulas with two different variables. So here are a couple common ones that we're going to be seeing. The most common one is going to be this first one. It's going to be a rectangle. So we have to know that the area of a rectangle is x times y, where x is the width and y is the length. And the perimeter is 2x plus 2y. So the perimeter is 2x plus 2y because we have x plus y plus x plus y, simplifying to 2x plus 2y. And then the next one is going to be a rectangular prism. And the volume is going to be length times width times height, x, y, z. And we should also know the surface area for this one. The surface area is going to be the area of every surface added up. So you would have to find the area of each one of these rectangles and then add them all up, and that would be the surface area. Next one, we have a circle. We know the area of a circle is pi r squared. The circumference, which is essentially the perimeter, is 2 pi r. And the last one, we have a cylinder. The volume is pi r squared times h. And for this one, there's also surface area for this one, but we'll go ahead and wait for that formula if we see it in a question coming up. So here's going to be kind of the steps for doing these questions, and we'll obviously do a bunch of examples. For this, a good idea is to draw a picture because we're going to be working with shapes, so drawing a picture is always good. And then you're going to have your two equations. So you're going to be deciding what quantity is going to be maximized or minimized. You're going to assign variables, letters to variables. I tend to use x and y the most. You can use whatever you want. And from that, we're going to have our objective equation and our constraint equation. And two equations, two variables, what we're going to do is we're going to solve for one of the variables from the constraint equation, plug it into the objective equation. That's going to give us one equation, one variable. Then we're going to take the derivative, set it equal to 0, and that's going to give us our max value or our min value. So let's go ahead and jump into some examples here. So for example, this question is going to be maximizing an area. You want to plan a rectangular garden along one side of the house with a picket fence, and the picket fence is going to be on the other three sides of the garden. And we want to find the dimensions of the largest garden that can be enclosed using 40 feet of fencing. So we have 40 feet of fencing. We're trying to create a rectangular garden, but we don't have all four sides for fencing. We're using the house for one of the sides for the garden. So you can see these examples right here are some examples of the garden that's going to use 40 feet of fencing. And you can see that the house is one of those sides. So these are some examples, So we're trying to find the dimensions of the largest garden. That's going to mean the largest area that can be enclosed using 40 feet of fencing. So you can see the area down here that's calculated. These have different areas, but the same exact perimeter. Okay, so those are just a couple examples. Let's go ahead and actually do this question. So we know that we have two equations. We have the area, because that's what we are trying to maximize in this case. So the area, let's draw a picture first here so we get our variables lined up. We have the house, and then we're going to have the fencing for the garden. And let's call this y, we'll call that x, and then we'll call this y. So if that side is x, that means this other side is x also, because opposite sides in a rectangle are equal. So let's set up our equations. We're going to have a equals, the area of a rectangle is x times y, length times width, and then we're also going to have perimeter. So perimeter is not 2x plus 2y because the house is on one of the sides. The perimeter is going to be x plus x, which is 2x, plus y. So here are our two equations with two variables. We know that our area formula is going to be our objective equation because we're trying to maximize the area. And then we also know that our perimeter equation is the constraint equation because we're told that we can only use 40 feet of fencing. That's the constraint, that is the limit. So we can rewrite this as 40 has to equal 2x plus y. Okay, so we want to maximize area. So we need to first get one equation with one variable. So that means we need to start with our constraint equation. We need to solve for one of the variables. It does not matter which one. And then we're going to take it and plug it into the other equation. It's essentially like the substitution method for solving equations. So it's going to be easiest to solve for y because all we have to do is subtract 2x on the other side. So we get y equals 40 minus 2x. So this one was the easiest to solve for. You could have solved for x. We would have ended up with the same answers, but this was the easiest. So we're going to take that and plug it into the other formula, and that's area equals x times y. We know that y equals 40 minus 2x, so we're going to plug that into the other equation. And let's go ahead and distribute that x. That's 40x minus 2x squared. So now we have one equation with one variable, and let's go ahead and take the derivative. So we're going to maximize this by taking the derivative, a prime, and this is just a polynomial, so the derivative is 40 minus 4x. We're going to take this and we're going to set it equal to 0. 40 minus, I'll just replace a prime with 0. 0 equals 40 minus 4x. We solve this for x, and we get 4x equals 40, so x equals 10. And let's verify that this is actually going to give us a maximum value. And to do that, we need to come up with a number line, just like we did previously. We put our value of 10, f prime down here, f up here. And now we plug in values. We can plug in 0, because that's going to be easy, to the left of 10. And then we could plug in 11 to the right of 10. We have to plug that into the derivative function to see if it's positive or negative. Let me just change f prime to a prime and then f to a. Okay, so we plug 0 in. 40 minus 4 times 0 is positive. So that's going to be increasing. We plug in 11. 40 minus 4 times 11 gives us a negative answer. So a is decreasing. So what happens, it goes from increasing to decreasing. That means it is a relative max. So we know that we did it correctly. So the last thing we have to do is solve for the other variable, solve for y. And we do this using the constraint equation, because the constraint equation already has y solved for. So it's going to be y equals 40 minus 2x. We go ahead and we plug in, our x value. So that's 40 minus 2 times 10, which is 20. So the dimensions that give us the largest area that ensure 40 feet of fencing are going to be 10 feet for x and 20 feet for y. Okay, and it's the same setup every single time that we are doing these types of questions. Two equations, that's kind of the tricky part, making sure you have the equations correct. Use the constraint equation and solve for the one of the variables, plug it in the objective equation, take the derivative, set it equal to 0, and that is pretty much it. All right, let's do a couple more. Next one is maximizing volume. And for this example, we have that postal regulations state that packages must have length plus girth of no more than 84 inches. Find the dimensions of the cylindrical package of greatest volume that is mailable by parcel post. Okay, so we already have a drawing drawn for us. We have this cylinder drawn, which is nice. So first, now we need to go ahead and come up with our two equations. So our first equation is obviously, we have a volume equation. So let's write that down. We know that that's going to be our objective equation because that's what we're trying to maximize, because it's the word greatest. So greatest, we know that we're trying to maximize volume. And let's go ahead and write down the volume formula for a cylinder. So the volume of a cylinder is pi r squared times the length. So pi r squared is essentially just the area of the base. It's the area of the circular base. So I'm not going to use x and y. I'll use r and l here just because that's what it's labeled as in the picture. And now we have this other formula, which is going to be the constraint formula. So the constraint says the length plus the girth can be no more than 84 inches. That means for it to be the largest, length plus girth has to equal 84. So setting this up using our variables, that's going to be L plus, so for girth is actually the circumference of the end of the package. Circumference of a circle is 2 pi r. So circumference of this is 2 pi r. And now we have our two equations. We have the length plus 2 pi r has to be 84 at the most. So that's going to be our constraint equation because we have a limit or a constraint on it. So there we go. There's our two equations, two variables. Now we need to solve for one of the variables from the constraint equation and plug it in the objective equation, take the derivative, set it equal to 0. So I think it's going to be easiest to solve for L from the constraint, and hopefully you agree, because all we have to do is subtract 2 pi r to the other side. So we get L equals 84 minus 2 pi r. Now we can go ahead and plug that into the objective equation's L. So the objective equation is V equals pi r squared times L. So now instead of L, let's write that as 84 minus 2 pi r. And I always recommend distributing. You need to distribute here. So distribute the pi r squared. We get 84 pi r squared minus 2 pi times pi is pi squared. R squared times R is R cubed. So now we have volume in terms of R only. Pi is a constant, so it's fine. Now we can go ahead and take the derivative. And we get the derivative, v prime, is going to be, so this is dv dr with respect to R. This is going to be, here's the variable, power rule. 2 times 84, we get 168 pi r to the first, minus 3 times 2 is 6 pi squared r squared. So the pi's are just kind of coming along for the ride here because they're constants. And now we're going to set this equal to 0 and solve it. You can see it's going to be a little bit harder for this one. So what we can actually do here, keep in mind that factoring is going to be helpful. We can factor out a GCF of 6 pi r. Factoring that out front, we're going to be left with 28 minus pi r. And then we set both of these equal to 0. So that's going to be either 6 pi r equals 0 or 28 minus pi r equals 0. And then we solve them separately. The first one, divide both sides by 6 pi, we get r equals 0. Hopefully we know that we can omit that one, because a radius of 0, that's not going to be a package, a parcel at all, so that's not going to work. And then for the other one, when we solve this one, we're going to add pi r to the right, 28 equals pi r, divide both sides by 28 by pi, we get r equals 28 over pi. And for our only other value right here, it kind of has to be this value because we only have this one value right here. But what you could do, you could verify that this is a maximum using a number line like we did before. I'll skip that for now. You can use a value of 0 to the left, and you could use a value of about, looks like 10 would work to the right, and verify it goes from increasing to decreasing like we did in the previous one, but I'll skip that. And then the last step here is going to be solve for L. Solve for the other dimension for L. And to do that, we have to use right up here, once again from the constraint. The other variable is always going to be solved for you because you solved for it before. And all we have to do now is plug in our value for r. That's going to be length is 84 minus 2 pi times 28 over pi. Solving this is kind of nice because the pi's cancel. 2 times 28, we get 56. And 84 minus 56 will give us 28. So that gives us our two answers. We have r equals 28 over pi inches and L equals 28 inches. And that's going to give us our maximum volume for that parcel. And you could, if you really want to, you could plug in 28 over pi in the calculator. It's just going to give you a decimal that goes on forever, so you'd have to round. So I'm just putting the exact answer here. Okay, let's do one more example. A canvas wind shelter for the beach has a back, 2 square sides, and a top. If 96 square feet of canvas is to be used, we want to find the dimensions of the shelter for which the space inside is maximized. So we're told that the space inside represents the volume inside. So we know that we're going to be maximizing volume once again. So that's going to be our objective equation. It's going to be volume equals, and then it's going to be the volume of this rectangular prism. So volume is going to be length times width times height. Notice that this missing bottom piece does not affect the volume. So we need to come up with some variables. We know that it has 2 square sides. So this side and this side, these are squares, which means if we let this be x, then this is also x. because the square's sides are all the same. That's kind of key to knowing, to being able to do this, that those are the same variable. And then we can let this length up here be y. So that means the volume is x times y, which is x squared times y. So that's the volume. Next thing that we need is the constraint equation. 96 square feet must be used. We know that's the constraint. 96 square feet. Square feet means it's an area, and this is going to be a surface area. So this is going to be a surface area of 96 needs to equal, and then we need to figure out the surface area in terms of x and y. So what we need to do is figure out the area of each one of these sides, the area of this side, the top, and the back, and add them all together. The area of both of the sides right here are going to be x times x, so that means it's going to be x squared, x squared plus x squared. So those are the areas for the sides, just length times width. And then the areas for the top and the back are both going to be x times y, because this is also an x right here. So length times width would be x times y. So that's plus xy. Same thing for the back. It has a length of y and a width of x. So that's going to be xy also. So we have our 4 sides added up. And what we can do is we can actually go ahead and simplify this a little bit. That's 96 equals 2x squared plus 2xy. Just combining like terms. And we know that that's the constraint equation. So now we can go ahead and solve this for, solve the constraint equation for y. And it looks like it's going to be the easiest to solve for y because there's only one of those y's in there to solve for. So we can subtract 2x squared to the left. And then we can divide both sides by 2x. And that'll give us 96 minus 2x squared divided by 2x. And let's make it a little bit easier on ourselves here and simplify that. That's going to be divide both of those by 2x. That's going to give us 96 over 2x is 48 over x. Minus 2x squared over 2x is going to just be x. So that's because the 2's cancel and x squared divided by x is just x. Okay, and now we're going to go ahead and plug that into our objective equation. And our objective equation was volume equals x squared times y. We plug in what we just found for y, which was this right here. That's going to be x squared times 48 over x minus x. Go ahead and distribute the x squared. That's going to give us 48x, because x squared divided by x is just x, minus x squared times x is x cubed. And now for the last thing, we just have to take the volume, take the derivative. So v prime, this is going to be power rule 48 minus 3x squared. And we're going to go ahead and set this equal to 0 now. So set this, I'm going to go on a new page. So setting this equal to 0. 0 equals 48 minus 3x squared. And solving this for, first we have to solve it for x squared, so we can add 3x squared to the left. Divide both sides by 3. 48 divided by 3, we get 16. X squared equals 16. When we take the square root, we're going to get plus or minus the square root of 16, which is plus or minus 4. But we know that we can omit -4 because we're talking about a length, so it can't have a negative length. Okay, so there's one of our variables. And once again, you could verify that this is a maximum. A relative maximum, you can verify using the number line, just like we did in the first one. I'll just skip it for now. So let's go ahead and solve for the other variable, which we called y. And we're going to solve for that one using this right here from the constraint, because we already have it solved for. So let's go ahead and solve for that. It's 48 over x minus x. We plug in x equals 4. So 48 over 4 minus 4, which gives us 12 minus 4, so we get 8. So those are going to be our answers, and the dimensions of these were in feet. So that's going to maximize the volume of that shape when x is 4 feet and y is 8 feet. So using those dimensions on that shape will give you the largest volume. Okay, so that is it for this optimization section.